Go ahead, Usman.
Yeah. Hello everyone in the center and people who joined remotely. Today I'm presenting this paper in beats. It's by Oreshkin, and you can see the last name and maybe it could get more interesting for you. So the paper is about time series analysis and mostly forecasting. And I thought it would be good for us because our data is also kind of time series. Although I don't know, someone is doing forecasting or not, but maybe we can do it. So like the basic idea of the paper is that you need to make a deep learning model do the time series forecasting and also not just forecasting, the results should be interpretable. So I thought like many people in this group are interested in interpretation, and then also we use time series data, so it would be good data for us. So so that's the basic outline. I'll go briefly through the introduction and what's the problem statement, what's the method, which is their model and weeks. The interpretability components, it's divided into two phases, trend and seasonality, because the time series they use, it mostly has two components, or there can be some other functionality in it also, but mostly there's a trend in time series and then there's also seasonality. And then briefly through the results and then what are the further works which are based on this paper. So first of all, introduction. Time series forecasting has a lot of application in different fields. So generally there are a lot of statistical models which are available for time series analysis or prediction or forecasting. For example, you have ARIMA, HMM, and these models are designed to deal with time series data. Like they expect that there would be a component of time in that. But if you look at the machine learning method, for example, decision tree or SPM, it's not typically developed for dealing with time series data. Like it can deal if you do feature engineering, like instead of giving the time series as input to the models, you can compute features such as mean, median, and other stuff. And there's a lot of literature available that what features what features you can extract from time series if you wanted to use a machine learning model. But typically the models which are used, the machine learning models on time series data, either they don't perform as good as the statistical models, or even if they do, it doesn't make much more sense, especially if your time series is not regularly sampled or there's some other caveats in the time series. And if it is performing very well, then maybe your time series is very simple and you can just eyeball for forecasting what's going to happen. So in the first place, you don't even need these models if they're working that well. Now, deep learning has some concept of layers, especially when you are using multiple layers or residual networks or RNNs. So there's a concept of sequence and time in these models. But the problem with that is that the deep learning models, they are not very interpretable. So that's a problem. And a thought on that is that who's to blame for this, that deep learning models are not interpretable. Like maybe they can be, it's just we are not allowing them to be, and we are just focusing on like plus metric results like plus accuracy and stuff. So the goal of this paper is to develop a deep learning model which beats the statistical models on time series data and provide interpretability. So that's the model, the architecture. It looks kind of vague, but it's very simple to look at. So if you start looking at it from the right side, yeah, they have a bunch of stacks. So just think of it in terms of like a ResNet, and it would make sense very, very quickly. So they have a bunch of stacks which are shown on the right, and the output of each stack is combined in the end to create a global output. And the figure in the middle shows what's in each stack. So in each stack, you have multiple blocks, which is shown in the middle figure. And then on the left side, it shows that each block has a fully connected stack, which has 4 layers. And then what they do is that they forecast to predict the future, and they do backcasting as well. So it's very easy. It's just a bunch of fully connected layers. And you can see that the HL1, HL2, HL3, HL4, L is the layer number in the FC stack, which is on the left side. So they have 4 layers. So you have 4H over there. So after that, the FC stack, they have 2 components. The first one is the theta F and theta B. So what those are, like they express them as expansion coefficient. So what they do is that first we will learn the expansion coefficients, and then we will learn the basis vectors. And combining those, we'll get the forecast or the backcast. So that's how they are dividing their model into different parts. So again, to get the theta F and theta B, they use a fully connected layer, which is, yeah. That's not my test, right?
Can you explain again? Sorry, I missed the beginning of explanation. So this blue block is one step, it's Markov, one step ahead, one step back, right? The blue block.
Not one step back. Actually, backcast is they try to mimic the input they receive. So
no, but that's your previous time point, right?
and that's your current time point, what the input you get. So whatever input you get, they're trying to predict that or just generate the input.
So learn to be an identity, right?
Yeah, so the idea is that from backcast, which you get over there, for example, you get X as input. So they try to mimic X as output, and this output is given to the next block. Not completely, what they do is that they take X minus what this model is doing, giving output as the backcast, they subtract that and they give rest to the block two. So the idea of that is they're saying that we are making each block learn something different. And once it has learned that, that part of input is no longer useful for the second block or the third block or the next block. So they subtract that from the input and give the remaining part of the input to the next block.
But all of the blocks in the stack predict next time point.
No, they predict what they need. So they predict 2 things. They predict the forecast.
Forecast, I'm asking about.
Yeah, the forecast is the forecast, but what they give as output to the next is what they receive.
Yes, but they also give forecast.
Yeah, so there are 2 residual connections. The first one is the backcast, which you subtract at each time, and the forecast one is what you add. What
is forecast? It's about the next.
Yeah, the forecast is the next.
So all of K blocks in the stack predict information about the same thing.
The same thing, and they
next
add,
step, Markov,
yeah.
basically transition
So,
1 step ahead.
So if you are right here, so what you get, you receive this as input. This is your X, and it will receive X and try to mimic X add, and then you subtract them and give the remaining part of X to the second block. Where the forecast is what you want to predict. So each block does a forecast, you combine all the output, and then that's the output of the first stack. Then you have the second stack, and that will do the same thing. So and so on.
I understand that the blocks actually are performing collaboratively, right? So as you mean that is subtracting the output to get input for the next block. Yeah, but what is the function of each step?
The function of
Each step. I understand the functions of block.
This one or
No,
Each stack is what he's
yeah.
okay, the function
Right,
of
each
each stack.
step. Yeah. How is it related to block?
So the way it's saying is that in the end, what they do is that they make each stack. Okay, if you remember, I said that these are modeled as the expansion coefficients, and these are the basis vector. So what they do is that in each stack, when they want to make it interpretable, they put some restrictions on the basis vector. So the first restriction, so they in the final model, they just have 2 stacks. The first one, they have restriction to make it learn the trend in the time series, and using the second stack, they make it learn the seasonality part or in the time series.
Okay.
So what they do is that they're also trying to make each stack learn a different part of the overall time series data. So in the end, they combine, and then what they look at the output of each stack, and that gives you the interpretability.
And the basis vectors are not learned, correct? They're just chosen.
They can be learnable. That's the generic model, or they can be made, put restrictions on them, and that's the interpretable one. So they have two variations of the model. And the generic one, they're just simply vectors or matrices, which is learnable. But in the interpretable architecture, they put restrictions on it.
But I don't understand from this figure still, is it autoregressive model? Is it going like step by step, take my previous output, generate the
It
next?
is a period, isn't it?
Something
I
like
thought
that.
It doesn't take like,
So
you know,
I understood that block one is replicating its input, and it is actually subtracting from the original input.
Yeah, this is irrelevant though. I mean, I understand that part. This is irrelevant. This is all about the same time point. What happens here? So I'm at T. Am I operating with T or I'm operating with V1 and V2? So V1 contains all of the time points before T. And V2 contains all of the time points after T. Or I'm operating with T minus 1 or T plus 1. And then I move and shift.
it's
What
kind
is-
of mixture of both. Like they, at each time point, they take a window, which is your top part, V1.
Mhm.
So for example, if they want to predict X steps in the future, they'll take N times X
Mhm.
input at each time. But it's not like the input you get over here, you make some prediction and that is given as input to the next sequence. No, you take some input, you predict and forget about it. And then at the next time you take another input and you predict and forget about that.
So you're taking block input
Mhm.
is a n time steps.
N times H, what you want to predict.
But in a way, you do remember it through the weights, right? Like it's
Yeah,
just more of like a.
It's
a
depends how you're
future
looking at the
extract.
model, like if you're looking in terms of blocks,
Yeah.
it is kind of,
Yeah.
you know, giving sequences. But if you look at overall and don't look at the weights or shit, then it's not.
It's more like a feature
autoregressive.
extractor, I guess.
Yeah,
Yeah.
it's more like,
So that it works with sliding windows basically, or could work.
it does work. Any other questions?
I mean, yeah, I guess you're gonna talk about the basis vector prediction. I'm still like confused about what that's actually.
Yeah, that's all I'm gonna talk about it.
Okay, yeah. If it's just arbitrary vectors, how do you know they're a basis, right? Was
You don't know their basis, but you are saying, okay, these are my bases, these are coefficient, but you are not putting any restrictions on it. You're just assuming, okay, this is, like you can, in the generic version, even if you don't have this part, like you can do this from these 4 steps, from this layers as well. You have 4 layers, you don't need this final one if you don't have any special restrictions on it. But later on for the interpretability, it makes sense.
Sorry, so in the general case, the basis vectors might not actually be
Yeah,
basis vector.
yeah.
it just makes sense, yeah.
Rogers has a question. Can you, Roger?
Thank you. So I was wondering, is there anything built into this model to prevent it from forgetting? Say if you train it in time series from subject 1 and then go to subject 2, train on subject 2, when you go back to data from subject 1, you forget about it. Does it have anything that prevents that from happening?
I didn't get that, like.
He asked if there's any method that it prevents it remembering training data from subject 1.
Not that I read something like that, no.
You reset the input vectors though, right?
Yeah,
Mhm.
I mean, it's kind of in the weights, but I guess that's with any
And that's the
learning method.
Okay, so in the generic architecture, it just the P, which they call the basis, it's learnable, so it's just a matrix of H time the length of your theta. So H is the number of time points you want to predict in the future. So that would be your matrix, and you just multiply it with data, add some biases, and you'll get your prediction, the forecast and the backcast. So YL is the forecast and XL is the backcast. So as there are no constraints are imposed, no structure is seen in the output. So which means there is no interpretability. The model is just learns some weights, which would reduce the loss. The loss is the prediction they make, the prediction and the true, the actual time series. So there's the generic architecture. And it performs well. It's not that it's not performing well. The metrics that they use, it still beats the statistical models. So if you just want to look at those, it's good enough. But for the interpretability part, they mentioned that what they do is that they add structure to the basis layers at the stack level. And what those structures are, it's basically just to the trend and seasonality, because mostly, I don't know about the fMRI data time series, but in other time series like for banks and other stuff, season and prices and everything, they are mostly two things. One is the trend and the other is seasonality. And if someone doesn't know what those are, so on the first row is the observed time series, and then the second row is the trend. You can see that with time, the values are going up. So it's called an upward trend. And then the second part is the seasonal, that after every time the model, it's cyclical, it's repeating the value. So YT is equal to YT minus delta, and delta could be the gap in the seasonality. So you combine the second one, the second row and third, you will get your input, your observed time series. So those are the two structures that they want to learn from the data, and they want the deep learning model to show you what the trend is in the time series and what the seasonality is in the time series, which the generic model does not do.
Sorry, I have a question. They add these two to the data or the basis?
They put restrictions, constraints on the basis, like over
Basis
here.
that generate the data? Are these
Not
the
the
basis
data.
that generate the data?
They don't do anything to the data. They just put restrictions on the basis vector, that the basis vector should represent something. They have two stack in the model. The first stack, the basis vector in the first stack, they put constraints on them, so it learns the trend. And on the second stack, they put constraints on them to learn the seasonality.
I see.
This is simulated data, right, that they're using?
Sorry?
This is simulated data that they're using.
I didn't read that much what data was that, but it's the data they use in some competition, and this was the winner of some of that competition. I don't know if it's a real data or just
So in the constrained version, are the basis vectors still actually basis vectors? Can you linearly combine them to make up the data?
Yeah. Yeah.
Yeah, because they're trying, so the base vector in this case are the trend and the seasonality, and you can literally see it's a linear combination. Okay.
Like this is not their model. This is not their.
No, I
I'm
know,
just
but more
explaining
like,
that you
this is
can
what
do.
they're trying to.
Yeah,
do,
this
right?
is what they're
Yeah.
trying to do. How much they do, we'll see now.
So if they were able to find those, then yeah, it's like perfectly.
Okay, so the property of trend is that it's mostly monotonic, like it goes up or down, and the other property is that it changes very slowly. So to do that, what they do is that they constrain the GF. So sorry, I missed. GF and GB are those function which learns the basis. So what they do is that they constrain GF and GB to be polynomial of small degree. So it's varying slowly across the forecast window. So if your forecast window is, let's say, H could be anything you want to forecast, 5 values or 10 or 15, whatever. So what they do is that once you have your theta, so over here, the S is the stack number, L is the lane number, the block number. So what they do is that they multiply that with T, where T is a vector going from 0 to H minus 1, the number of values you want to predict. And they make it polynomial. So, and they choose a small degree of polynomial, so like 2 or 3. So what would happen is that let's say your P is equal to 2. And so that would make, since it's starting from 0, your theta would be of length 3. And each time what you will do is that you will multiply, let's say your theta 1 is, let's say 2. So you multiply that with the t vector, which is changing through time. And for the first time, it's ti, so I would be 0. So it's basically 1. So you just get what your value was. For the second time, for the second degree, for I is equal to 1, you'll get this vector. And when your I is 2, it will take the square of this. So it's changing across the time, and because it's a small degree, it replicates what trend, the property of the trend aspect in the time series. So that's how they make some constraints on GF and GP. When moving to seasonality, what they do is they simply use a Fourier series, because seasonality is regular, cyclical, or recurring fluctuation. So what they do is that they constrain GF and DB to belong to a class of periodic function. So for that function, they use a Fourier series. Again, it's very simple to look at. For the first part, for the first half, because let's say if you want to predict forecast H values for the first half, they use cost function, and then for the second, they use a sign in the mixture of that. That will give you the seasonality. So that's how they, and remember this theta forward is the coefficient, they model it as the expansion coefficient. So this would be, in this case, your basis is t, and in this case, the bases are the Fourier series.
So I don't, first, is the coefficients here complex?
Sorry, what?
The coefficients here, are they complex? Are they complex number or are they real number?
No, they are real numbers.
They are real number. Okay, so this can't be Fourier. And the previous one, go back. So is t time? This is time?
So t is a vector, yeah, you can think of it, it's a time for the number of values you want to predict, and the number of values you want to forecast from your current t.
So for example, they are saying t powered by 2 is trend. Because trend is t powered by 1 usually, right? It's just something that changes with time linearly. But they are essentially saying all polynomial orders of t is trend 2, because
Yeah, so
you
what
said
they
that
do
this
is
is the
that
trend.
the polynomial value they choose, the p value they choose is 2. So it's
2?
0 and 1, and then, yeah.
Okay, so they're calling T2 trend 2. Okay. Okay, thank you.
Okay, so that's it's not that the model is very difficult to understand. It's really a relatively simple model. So these are the results. They do use 4 data sets, and the bottom 3 are their models. The G is the generic one, I is the interpretable one, and the I plus G is what they do is they use different ensembles, and then they combine all of them on the test data.
I'm sorry, I missed what the interpretable part was. Is it the basis vectors that are the interpretation, or?
Yeah, so what they do is that since they have 2 stacks, one is mimicking the trend and one is seasonality. So the next slide I show you how it's interpretable. So
From my understanding, for the non-periodic model, we're kind of doing something like a Taylor series representation of this thing to a limited degree. It's like some just polynomial up to a small degree, but it's and then they use a Fourier series for the periodic, which kind of makes sense to me. You could use Fourier for non-periodic as well, but it would be weird.
I think it's funny that they're OWA measures. I mean, because it doesn't really matter, it's all the same model. But without standard deviation, it just seems like they're almost exactly the same. Like I can imagine that the standard deviation here is probably not going to be 0.000001 or something. Seems a little bit, close to each other. It doesn't seem like there's a lot of difference between the models that they have.
yeah, like I said, in terms of the classification score or whatever metric they are using, The generic version is not that far from the interpretable ones. It's
But you
the
get
same thing.
interpretability.
Yeah. So the generic version is already beating from what they're comparing to, but the main advantage of what they do is over here. Okay,
What is
so sorry.
what are these other models? What is a
The
statistic? Is
top
that
one, the pure ML is it's a paper where they call their model pure ML, and the statistical model it's also a paper which they use as test stat-based model for these data
so
sets.
what is it? Is it ARMA? Is it or what is that a
I did
statistical
not
model?
check basically that. I didn't check what the statistical model exactly was. I checked the ML one, and in the ML one, what they do is that they use machine learning and they would combine the statistical models, both of them they combine for the prediction. That was the MLDS combination was, I think, the winner of the competition before them, and that what they were trying to be.
It was Wiener filter or Wiener. Oh, okay.
Yeah, they explain it in the paper that the model they were using, the MLDS model.
And the data that they used, they are seasonal, right?
Yeah, it has both concepts, trend and seasonality in there.
Well, I don't know what that is really important, what the statistical is. But if, for example, statistical is something like, I don't know, ARMA model or something, they are cheating because they are essentially saying that the data is seasonal, right? And they are essentially fitting a something like short-time cosine transform and learning the cosine coefficient at each window, and based on that predicting. But comparing that to the, for example, a normal statistical model who doesn't have a periodic set is, well, it's.
Yeah, I didn't focus too much on the models they are comparing to. My main goal was how they're making it interpretable.
They use
So, I don't know
ARIMA, auto ARIMA, and in general, the unified state space modeling approach that can be used to explain and analyze all of the approaches mentioned above. And then they cite a paper for an overview.
Yeah, but those are stationary.
Yeah.
The signal is non-stationary. So.
Okay, so the main thing that I want that for this paper is this. So this is the different inputs, different data set they have. The blue one is the actual time series. The yellow one is the forecast by the interpretable model, and the forecast G is from the generic model. And they divide, since I mentioned they have two stacks. So this is stack one from the generic models, the second stack from the generic model. And then this is the stack, the interpretable stack, which is modeling the trend. And this is the interpretable stack, which was modeling the seasonality. So if you look at this one and this one, basically both of them are outputting the same thing basically, or in each of the case. It's not like one is remembering some trend, the other one is remembering some seasonality. It's the mixture of both of them. And the min and max values is always the second stack, the minimum and maximum values are much lower than from the first stack. Whereas when they do the interpretable model, where one stack is for learning the trend and one stack is for seasonality, it shows that this is exactly what the stacks are doing. So this is the actual time series, the blue one. We can see the trend is going upward. Over here, the trend is also going a bit upward, and this the trend is downward, and then there's also seasonality as well. So this stack, you can see that this is learning the trend, which is going down in time in the actual time series. And the second stack is learning the seasonality, which was present in the time series as well. So like that's the overall, I think that's the bigger contribution of the paper. That instead of just assigning learning some parameters of weights, they put some constraints to make a model learn something which can be interpretable in the end. So there's also further work done on this paper. The second one, and hits, is fairly recent. I think it came out in February. So the difference from this paper with the first one is that since this model is working on univariate time series, the n bit x, they take all the other parameters as well to make it multivariate. And the n hits version, what they do is that they sample. It's not entirely regularly sampled, but they use different rates of input from the time series to mimic some kind of irregularly sampled data. Why I chose this paper is like I wanted to, like, it's not very difficult to explain, so I thought maybe we can spend less time on explaining the paper and more about that, the fact that how if a deep learning model is not being interpretable, so is it the model's fault, or is just our fault because we're just looking at like classification accuracy or some other metrics or loss or cross entropy loss. So if we're just focusing on those, then we know that probably the model is not going to be interpretable. Like in basic example, like no one told me once that if a model wants to classify aeroplanes in the picture, it can just look at the background. So the model is always going to find some easy way if you just want to do accuracy. So instead of just focusing on accuracy, we need to put some, not constraints, like they put some constraint, maybe some people don't like that word, that like we shouldn't put deep constraints on deep learning model and it should learn everything on its own. But I don't see how, because even when humans are learning, we put some constraints on that. Like, I don't know this example would fully convey the meaning, but when I was small in school and back home, we are asked to memorize the tables, like 2 times 1 is 2, 2 times 2 is 4 and stuff. So I didn't like remembering all of that. So I just figured out one day that you can just add numbers and you can get the result on.
I still don't know.
I think the problem isn't so much imposing constraints as a general concept. Certainly there are maybe radicals who would say that that's always bad, but it's the choice of constraint to me seems very arbitrary and selected to this particular data set, right? Versus the problem of estimating a basis function seems like the kind of thing that you could do with a more principled set of constraints, right? I don't entirely understand why their choice works. Maybe if they have justified it, saying, okay, you can expand any function as a Fourier series, which is true, better for periodic functions. Maybe you could justify to me why a network could learn a certain form for a Fourier series, but yeah, their choices here just don't seem to make particular sense to me.
Yeah, when I had other papers which I could have presented, like neurology and statistics, but they were too, like, I thought that almost all of the time would be spent to explain the paper. I am not saying that this is a very great model or anything. And
I'm not criticizing you.
Yeah,
I'm criticizing
no, I'm saying that
it's
it's not like we should use this. I'm just saying that the choice they make, that instead of just focusing on, let's say, accuracy, we should focus on like why, maybe some interpretability, and then it would start. Like, as I was saying, I just figured out you can add numbers and I get full marks in the test. But one day my father figured out that like how he is not making any mistake. And then he randomly asked, okay, what's 13 times 6? And I didn't know that because I never memorized it. So I used to add it. So he figured it out, and then he, like, in the way you can see that he changed the loss function. Instead of asking me one by one or giving me a paper to write one by one, he just randomly changed the loss function, and then I had to memorize. So maybe instead of, if you start focusing on, like, don't care about accuracy, which could be hard because then your papers won't be accepted. But focus more on that the results should be interpretable. And if the results are not, then we don't care about it. And
Well, maybe it's another form of regularization.
sorry?
It's another form of regularization of the model.
Oh, yeah.
So we use constraints even when we only care about accuracy. So most like in the field models, like most AlphaGo, the thing that beat chess, the thing that tells you what baked good is in the picture, like everything that's in the commercial sector, it's not just a deep learning model. It's not just a bunch of matrices and nonlinear functions. It's a mixture of things. AlphaGo is right, it's a hierarchical tree. It uses deep learning, of course, but these things are mixtures.
Well, specifically, AlphaGo actually uses things from learning in animals to try and kind of constrain it towards what it thinks is probably a better way to learn these things to come to a better solution. And part of the model are unconstrained, but the way it communicates between those models and the way it trains the model and the way, because everything,
Yeah, absolutely. And so this, I think researchers have this issue where we're just like, oh, make the new fancy deep learning model and put all the things in it and have it do all the and it goes nowhere, and we publish it. We might even publish it in ICLR or whatever, but then it goes nowhere. It gets cited by maybe, in the case of this paper, probably several hundred people over the course of its life, but it won't mean anything. Nothing will come from it. And we'll keep fighting this uphill battle. When really, if we took a cue, and I don't often say this, but if we took a cue from industry and said, let's take a step back and think about what actually works, instead of just like throwing kind of sometimes maybe bias data or just small samples or just small segments of the universe at a model and then publishing it.
But you're so contradictory now,
Of course.
because what actually works means the whole universe. That phrase, it could mean anything. What actually works? Yes. What brings me money? Easy in industry. What do you mean? What actually works? Here, when you're not in industry, but when in science, what does it mean? What brings me knowledge? What does knowledge mean? Can you predict now what knowledge means in 20 years, as you want your paper to matter, at least in 20 years, right?
Do you think,
I'm just trying to bring your attention that it's not as easy as you make it sound.
do you think that most papers that are published will be even considered in 20 years?
Do you think, your question,
Most
with
papers
regard
are
to the
not
following,
considered even today.
your question to me sounds like, do you think that most steps, physical steps that I make now matter in 20 years? And my answer is yes, your body is moving, you're alive. Every step you take now will matter in 20 years. Because if you don't take any steps right now, you will die.
I guess as long as it'll keep labs open in
We,
20
we
years.
don't. I think
That's the argument. If it brings in money so that we can maybe.
I think we don't
You
know.
are saying it brings the money. You're asking us, let's be like this.
money, like AlphaGo isn't necessarily about money, but if it.
Oh, AlphaGo is worse. AlphaGo has the game to win. There is very easy objective.
It's very clear.
Yeah, it's very clear.
But I would suggest that the steps that we take don't actually add to our knowledge base.
So
Maybe, yes.
no, the thing is, I don't think that we should talk about future, because researchers are really bad at knowing what sticks and what not, especially engineers. We have shown so many times that we don't understand. So I don't think it's to say, oh, 20 years from now, right, what sticks and what's not. But I think your point is more about that we should make sure that it matches our current.
Did you
How
see
it
that
is
video
our
of
current
Jack Ma
literature.
and Elon Musk where they're having a talk? It's-
Okay,
But
Elon
I
Musk
have a
is-
question actually about.
it's
I have a
hilarious.
question about this paper. So correct me if I'm wrong, they essentially just learned the coefficients of cosine transform and fit it on a data that is harmonic and
Yeah.
call it a day. Is that what all they did? I mean,
That's what I was saying, Ashkan. You know, I like this idea of using basis functions as a way of interpreting this like function
But-
estimation problem.
but
That is
not
a fine-
cosine and not cosine and sine. It's been solved for 400 years now. I mean,
Right,
the issue
yeah. Yeah.
The issue right now is that a lot of issue and a lot of people in a basis, people who are working on basis, that well, cosine and sine, the whole Fourier transform is not actually interpretable a lot of time. Yeah, you can explain everything using Fourier, but it doesn't mean that that thing is made of those cosine. It doesn't make sense. So, but just using cosine and sine is, I'm pretty sure if I understand correctly, you just run short time Fourier transform using the same window length and cut the signal into four times and use 3 of them to train the Fourier transform coefficient and then predict the other part. I mean, this is what they did, and you don't even need the trend because the trend is part of the Fourier. It is the first essentially coefficient.
I think you're right, Usman.
That's literally
Oh,
it.
sorry, right.
No, I think that is what they're doing in this paper. They are just, the only thing they're estimating are the coefficients for the Fourier transform.
But how do they get 4 features rather than just a sorted list of basis functions again? They also estimating how to combine the basis functions to get the trend, to get like first sinusoid. Like they're not the outputs. Can you scroll where you're showing
They
the
only have
graphs?
two features, right?
Those are not basis functions that they used. Those are combinations.
Sure.
So well, but everything is a combination of Fourier basis function. Everything.
And that's what I'm saying.
So, but they're returning a cup. They're returning all, it's a combination of basis functions as well, Fourier. But they are returning like, well, this is meaningful, sorry.
But their argument for interpretability, I think, still falls away because they're just saying this is interpretable because I chose basis functions that make sense for this problem that are interpretable.
No, but this is not basis functions. They're not outputting.
No, I'm not saying this is basis functions.
But they're
I'm saying
saying
that
this is
underlying, that
interpretable.
the constraint they imposed on their model is that there's this underlying, harmonic basis function that they can use to combine in a certain way.
Yeah, but that's
to
just a
forecast
tool.
well.
It's not because, it's not, that's why the model is interpretable. They're saying, my read is because you're looking at this and this is interpretable, what's on the screen. That's why the model is interpretable. Not because the Fourier basis is interpretable.
Yeah.
Fourier basis is universal, you can represent anything and everything. But like, do you understand how they combine? Like to get the sawtooth, you need infinite number of coefficients for your basis.
Not necessarily, you don't need infinite. I do not understand. Just use a sliding window, calculate short time Fourier transform, use 75% of data to estimate the coefficient, and then predict the other 25%. If that window length is selected the same as what they did, that is what they have done essentially. All of their fancy thing is just goes back to that. The way that they have learned for the sinus and cosine, for the sinusoid and cosine is based on that. What they did essentially, they are assuming something about the data. You just pick your coefficient, your Fourier coefficient in such a way that has the same resolution as what they did for cosine and sine. You will get, you get the better result. I have no idea. Right now, the issue of these is that we want to go beyond something like sinusoid and cosine. That is the question. Not we cannot learn sinusoid. I don't understand that. This data set is nothing important. It's seasonal data is not that hard to solve because it's periodic, right? That is not the issue right now.
If they had a method
Or
that
I
could
missed
estimate an arbitrary basis in a principal way, I think I would also be more convinced of it.
Yeah, I mean, that is the question right now. That is the goal. That is the final goal right now in people who work in this kind of transformation, in EC at least.
Yeah, normally we even detrain the data for fMRI.
Yeah.
So we didn't want to find it.
Yeah, but sometimes you, especially with weather and stuff, you worry about trends.
No, for sure. I mean, I understand. I was just like thinking about how you would even apply this to fMRI, and then I was like, that trend kind of falls away already.
No, it will not pop up in the result. But I'm still not clear how they like combining those cosine coefficients to get 4 groups.
I think it's like blocks have those things, and then they sum them together in a way, right?
Yeah,
And that's
yeah,
like
it's
the
like
stack, and then they stack together.
It's like each block.
Yeah,
has
so
its
they
own
are
basis.
building those.
Yeah,
That's the way I think.
But because it's again Fourier basis. It could be an elephant and a hare and something like whatever, right? They could find the patterns in the signal that make sense to split the signal.
But I do agree with Ashkan and Brad that they should probably use aperiodic and more complex and interesting data than this, because here it seems almost like, okay.
You
but-
can just eyeball it, like you just see at the actual time series, and you can just predict what's gonna happen next. It's not very.
No, for
Oh,
sure.
yeah, this is all toyish. It
No,
looks
no,
like
I
a
agree.
workshop
I agree.
paper, right?
It's like clear now.
How? I mean, I don't know.
Conference.
It looks very, very toy.
It's because Bengio conference.
Some reviewers don't care if it's just a toy, some really do.
Because
I think the reason is that they beat the last best model for this competition. Maybe that's what got it in.
The competition is fairly major.
But is this all the data they use in the competition, or?
No, I don't think so. It's all of the what they used in the competition. I think maybe this one just showed better graphs than showing that one.
But they were better than competition. So maybe Ashkan, you should just take a good old Fourier transform.
Yeah,
for
but
that.
I
So,
thought
so
it's
actually, I was thinking this paper is really essential. I'm looking, so essentially they said we have two set of bases. We have set of T0, T1 and T2, which because you cannot explain, for example, T1 and T2, especially in using sinusoid, it's hard. You have to have a very low frequency, which means that you have to have a very long window. So for example, T powered by 1 and T powered by 2 is really hard to explain using Fourier transform. So they have said our data, what is the issue? It has trend and it has period. So we essentially define two sets. One set is T0, T1, T2, and we do it by sinusoid. Of course, the result is better because that is the data. So, but the issue is that we do not know the bases. It's because right now I am seeing they are essentially saying that they are getting the DC right part, the T1 part linear trend, and the T2 part the power trend, right? They are removing that from Fourier, which then, because Fourier, if you want to get a Fourier with, for example, a very good DC or a very good linear trend, you have to have a longer and longer time series so that you can have a higher resolution frequency, because that's how it works. You have to add a lot of Fourier coefficient to get a line, essentially, right? But they said, oh, that is the issue. So let's have
that's
a
my
two-set.
comment about the sawtooth. For sawtooth, you need a lot of basis functions to get it really well. You need infinite because of the sharp corners.
Yeah, they have removed that. They have removed line from that. But that is not the issue. That is absolutely cheating. You
No,
cannot
look
say,
at
oh,
B stack 1 G second from the top on the slide. How are they
the
getting?
sawtooth. The sawtooth. You are
Yeah.
saying the sawtooth, right?
Yeah,
The sawtooth.
They have removed the T1 as another basis. So they have two set of bases, one Fourier set of bases and one T powered by a number set of bases, right? The issue with Fourier explaining something like sawtooth, as you said, or line, not even sawtooth, line, you need a lot of, because in Fourier, the number of time points that is available to the Fourier determines the resolution and frequency, right? So to get something like that, you need a lot of time points, right?
No, line is easy, by the way. For infinite period, you can get your line, but
no, you cannot. I can show that to you. For line, for example, if you want to get a line.
but the corner is hard.
No, line is hard to, because cosine, all Fourier is all cosine sine. Cosine sine are all had curve. You have to do something so that curves are become line. For that, you need to add a lot of coefficients, which means that you should have a lot of coefficients, which means that you should have a lot of resolution and frequency, which means that you should have a lot of time, because you cannot have
If you
more.
want line everywhere, that's true. But if you want line within your window, it's just a part of your cosine. That's what I'm saying. Part of your cosine of a longer period. But if you want a line everywhere from minus infinity to infinity, then you are right.
So just, yeah, but to get a good resolution for estimation of line using Fourier, right? You need a lot of Fourier. You need more and more. That is the issue.
For minus infinity to infinity, yes, but if it's windowed, then it could be different. But that's not what I mean. That's not the point of discussion. So the point of discussion, I thought, is like, okay, well, if there are classical methods that you can win this competition with, is it restricting us?
You can't.
Yeah,
The
you can.
competition, it's very high powered and it's a big deal that what they beat. So it's not just easy that you use a Fourier transform, put it like give it here. You can try, see what happens.
Yeah,
It's not
see,
that
it means we don't understand something about, the prediction. So prediction is still difficult.
I think I understand it. They essentially have said because the data set is based on two sets, two sets, right? Instead of one set, instead of just Fourier, it is two sets. You can explain it using a T powered by something and Fourier. What they have done instead of saying, okay, instead of only working on Fourier or this set of functions line, we include both of them.
like even if you don't forget the interpretability part, look at the generic part, it's not doing any Fourier or anything, it's still beating the state, whatever was in the competition.
Yes. So it's like
it's not just like they doing the Fourier, even if you don't do it, I think what they do is about making the two residual connections, subtracting the input instead of adding. What happens in resonant is subtract and making each block learn something different. Even that the generic version where there's no Fourier thing or anything or the trend, they still be what was state of the art at that time when they ran into the competition. So it's not that
Which one is the generic?
The general is that they don't have any constraints of Fourier or anything. The basis vector are just the just matrices which are run through backpropagation, and that's still getting whatever state of the art was which won the competition before that. So it's not that they saw the data or they just trained in it and there's seasonality in it. Okay, take one component for Fourier transform for the seasonality, take one for it's not just that. And maybe in this figure, what they showed is that they just have this too, but that's not all the data that they had and in the competition. This is just an example of what they achieved.
Yeah. So exactly, I think we're.
So sorry.
No, go ahead.
They've added an interpretability mechanic, which whether it's good or not, okay, whatever. But they're not necessarily resolving the issues of interpretability that we already know exist. You mentioned shortcut learning, essentially. That's a big issue. Under specification is an issue.
Yeah, they're not solving those issues. They're just saying that maybe you can train the model in a different way, which
No, shortcut learning can be solved because when
No,
you see.
sorry, but this paper is not handled.
Oh no, like by interpretability, it's like, hey kiddo, how are you doing this multiplication? Oh, that easy. I'm just adding the numbers. Okay, well, I know this is a shortcut learning. Show me what you're doing. And, okay, I'll look at it. Yeah, this is a shortcut learning. I see.
How do you solve it?
Oh,
That-
well, at least you know it's happening.
No,
We don't even know
no,
it's
that's-
happening
that's-
now.
In the sense that interpretability is a solution to that, sure, but this mechanic itself does not reduce shortcut learning. Sorry. So if they're not handled, like we already have mechanics that add interpretation. Attention.
Usman's example about himself makes me think that shortcut learning is irreducible. It's the property of a neural network.
Yes, the human being.
We just need to be able to recognize it because we do that all the time.
Yeah.
Shortcut learning, we do all the time. Why would I suffer through this table?
But
when
some
I can sneak a calculator on the exam.
Some shortcuts are spurious,
Yeah,
right?
yeah, it depends on this type of shortcut. I mean,
Yeah. So
That's
there's
the
like
issue.
No, yeah.
Yeah.
One thing that just to circle back to your main point, I think, I have been writing about, hopefully it's gonna come out soon, and thinking about making it formal in a paper as well, to talk about doing these types of things where you constrain yourself to make neural networks more aligned with what we already know about the brain, instead of picking things from the natural image space and applying it to neuroimaging. But to think about, wait, we know so many things already about the brain. How can we incorporate these constraints to make one more interpretable, and two, to help us to kind of like narrow down the solution space so that everything is hopefully more interpretable, but also more reproducible, right? Because things like convolutions, it's a I've said it a few times to other people as well.
Yeah, look, if you look at like autoencoder and variational autoencoders, Harsh is here, and I don't want to say anything wrong about variational autoencoder. Okay, so like in autoencoder, what we do, we just reduce the dimensions up to a certain level and try to see if that reproduces. But in variation autoencoder, we enforce that, like there's some constraint. The first one is its distribution. We put a constraint on that. And then instead of just learning some representation, we say, okay, we'll learn the mean and variance. And then with the mean and variance, it's interpretable. You can change the mean a little, and for MNIST, it would start giving you different numbers. You can change the variation. So there's some interpretability in what the model is learning, because we put some kind of constraints on it, and it makes more sense. So if we want the deep learning model to learn something which is explainable to us, like the features which deep learning model gives doesn't make sense to us, but it makes sense to it. That's why it's doing classification. But if we want something to make sense to us, we need to maybe enforce it somehow and not just look at like classification accuracy.
No, I agree with that. But that also involves using things that we already know. So for example, convolutional layers, for example, to predict mental disorders. There was a recent paper that Usman linked that basically said from structure MRI, we can't predict depression even with 1 million brains, doesn't really matter. Apart from that fact, but like result, I think there is some, you can argue about why, if convolutions may be logical for brain data to predict something like mental disorders, because it's translation invariant, but the brain is not translation invariant. There's different regions that have different functionality. I mean, I've said this before as well. I mean, but I think those things are interesting to think about.
I'm trying to translate and still be myself.
It's interesting to think about those things, right? Because we use models that are coming from natural images, and they work really well on that space. And to some degree, for some tasks, also in neuroimaging. But the question is, should we maybe be thinking about creating our own set of models that are based on neuroscience research, like we've been doing, I guess, before as well? It doesn't mean that we have to completely stop doing that, but it's more like, I think part of it is ease, like using convolutions to implement patching. It's also just easier, it's like.
Maybe if there are isomorphic, why not? But just 1 second. People, if you need to disconnect, go ahead and disconnect. We will continue the discussion because it's interesting, and we'll keep recording. Yeah, but if they're isomorphic, in a sense, then we don't care, like if they're captured.
But for example, if you think about it in brain regions, already things may be more interpretable, right? If you get features in a deep learning model where you can say, okay, these relate to a certain region in the brain, that makes it much easier, at least for also people for the rest of the field, to imagine what you're actually talking about when you're doing these classifications, for example. And I also agree with you on the BAE. That's actually why I work a lot on BAEs as well, because I think it does help that you can do some sort of like interpolation and look at these latent dimensions and see, hey, what is this actually learning? How does this map back to the brain space? What can we say about these things? Or have these things been reported before? Does it make sense from like a neuroscientific perspective that these brain regions are different, for example, between males and females, or between two groups? Yeah, I agree with the general idea that interpretability, I think, is very key also to neuroimaging.
And also other things also, like I feel that just we need to, so far deep learning has, like we have made models which can do what we do, like image classification and stuff. So far it has not increased our knowledge. Like we already whatever.
No, that's exactly what I mean, right? So like we already know what a dog is. So if it does it correctly, we just assume that it's doing what we're doing, which is what a lot of work is based on now, saying like, oh, our deep learning neural networks doing exactly the same thing that we're doing in the brain. But for neuroimaging, the problem is we don't know what schizophrenia or looks like. And if we get a high classification accuracy, that is, maybe a good sign, but then, okay, but then what does that tell us, right? Like how? So what is it,
Like
what
if
is
you
it
look
seeing
at-
that we're not seeing?
Like even if, I don't know, I'm not sure, maybe I'm wrong, like even if the doctors, they look at fMRI, I don't think they can tell it's
No,
schizophrenia
no,
or like,
As-
so, but the
I
model
can
is
tell you
doing.
that doctors don't look at it,
Yeah.
right? They psychiatric
So-
too.
So our models are doing it, but now I think we need to like increase our knowledge, like how it's doing, maybe there's something. Yeah.
Exactly, because then you can plug it back into, like, for example, if you were able to reduce fMRI to some metrics that you can, I talked to Noah about this yesterday. If you can reduce it to a few metrics that a doctor can understand, like, okay, there's some sort of activity in certain brain regions that we don't expect, or that are different from what we expect, then maybe, I mean, it shouldn't be that maybe those brain regions automatically mean some sort of like mental disorder or something, or are a biomarker for something, but it's something that maybe a clinician can be helped with, because it is extra information, right? And it is the quickest sort of short-term effect that we can have on the clinical side, I think.
Like, even if the model is just doing some shortcut learning for the disorders, that's even useful for us because right now we can't do that. So even if we know a shortcut for
I
learning,
mean, head motion is a very big shortcut for a lot of,
yeah, but yeah, in
Brain
most of the
density,
data,
that's
we
more.
reduce we discard the samples with some head motion, which is much more. So-
yeah, but even if you use the ones with head motion is a big predictor for certain sort of people with certain mental
Yeah.
disorders. Just move their head more at the scanner, which then the question is like,
It beats most of the most of other predictors. So
Features, yeah.
it's sometimes a better predictor, yeah. So that's why it's important to know what we're picking up on, because if we're just picking up on head motion, we can also just take this .text file that we get and then just predict directly from the head motion .txt file, which is, I don't think, you know, if it's a legit feature like that, it's really something you can say, yeah, this is super replicable and people with mental disorders move more, but you know, it's, the question is like, yeah, because a lot of the things that we do, for example, in pre-processing are often linear or close to linear, even if they're like a little bit nonlinear. And if you have a super nonlinear feature extractor that can learn theoretically every function like a universal feature extractor, it can just maybe find still, even if it's filtered away, those head motions, because it's easier to predict based on those than on anything inside of the brain, for example.
Okay, well, that's an interesting discussion and I wanted to record it, but let me stop the recording and call the meeting.